Now that we have u-substitution, we can arrive at this standard table of integrals, which if you look at these are essentially just using u-substitution, but we see these integrals so commonly that we can essentially memorize what the u-substitution would be rather than doing it each time. So look at number 1 there. The integral of cos ax dx is 1 over a sine ax plus c. Right, we could do a pretty brief u-substitution with u equals ax and get that, but it may be quicker to just go straight to this integral, straight from memory, and do it that way instead. So I recommend setting to memory or internalizing at least 1 through 10 of these. Now number 11, the way I see it when you're starting to go into arcsecant territory, there comes a point where you just look up the integral in a table of integrals, and they have these massive volumes that are just tables of integrals, essentially whole books full of integrals. And when integrals get too complex, either you use some kind of integration computing device or you look it up in a table, but you don't just memorize ever more integrals. So personally, I kind of stop it at 10, but you're more than welcome to memorize 11, and then you could also memorize integrals for involving arc cosecant, and just on and on it goes, right? It doesn't really ever stop. But at least 1 through 10. I would say a lot of these are pretty self-evident, but let's take a look at 8, 9, and 10 together and prove those, because those look a little more involved. Okay, for number 8, we have the integral of b to the x dx equals 1 over natural log b times b to the x plus c. That's what we're trying to show here. The first thing to note here is that any number b can be written as e to the natural log of b. Okay, why is that? Well, e and natural log are inverse functions, so they undo each other, leaving us only with b. With that substitution, this integral becomes the integral of e to the natural log b, and then we still have an x up here, so times x dx. And we know what the integral of e to the u is, so let's let this natural log b times x bit up here be our u. So our u is natural log b times x. Natural log b is just a constant, so then du is natural log b dx. We solve that for dx to get dx equals du over natural log b. Subbing this dx in all the way up here, whoops, right into the dx there, gives the integral of e to the, also subbing in for u, e to the u du, and then we have over natural log b, which I will bring out to the front here, natural log b, because that's a constant. But we know that the integral of e to the u du is simply e to the u again, so this gives 1 over natural log b, e to the u plus c. But recall that u is actually natural log b times x. So we can write this as 1 over natural log b, e to the power of natural log b times x plus c. And remember that e and natural log undo each other. But this x is still up in the exponent. So this is kind of weird here, but what we're left with is 1 over natural log of b, and then we just have a base b, but the x is still up in the exponent, plus c. And that's what we wanted to prove. Just a quick aside, as I was editing the video, I realized that it might not be completely clear how this works. So when we have e to the natural log b times x, due to the properties of exponents, we can rewrite this as e to the natural log b all to the power of x. That's the crucial step that I didn't explicitly state. Well, we know that e to the natural log b is simply b, so this gives us b still hanging out, but this x is still just out by itself in the exponent, thus we have b to the x. Just a little clarity there. Let's take a look at number 9. For number 9, we have the integral of dx over a squared plus x squared equals 1 over a times arctan x over a plus c. That's what we want to show. And we can kind of see with this x squared down here that we're probably going to have some kind of arctan. The key with this kind of integral is to factor out the a squared. So right off the bat, I'm going to factor out a 1 over a squared that leaves us with dx over, well, we factored the a squared out of the denominator, so it's just 1 here, plus, but when we factor something out, we're dividing each term left behind by that function. So this becomes x squared over a squared dx. Now it looks like we're making it worse, but note that we can write this as 1 over a squared integral dx over 1 plus, how about x over a quantity squared. So now we can jump in with our u substitution and let our u be x over a. Okay, then du dx, or you can just write that as du and bring the x up automatically, is 1 over a. So then du must be 1 over a dx, and then dx must be a times du. That's what we're looking for here. So we have our u and we have our dx. We sub all that in here to this integral, which gives the integral of 1 over a squared. Dx was a du over 1 plus u squared, because remember u was x over a. Well, now we get some nice cancellation. We have 1a up here and a squared down in the denominator there. So we get some nice cancellation, because remember, essentially a can come out of the integral because it's a constant. So this gives 1 over a integral du over 1 plus u squared. Well, we recognize this integral as arctan of u, so we have 1 over a arctan of u plus c, and 1 over a arctan. Remember, to back substitute, u is actually x over a, so we have x over a plus c. That's what we wanted to show. It's useful to know how to prove these just in case you're ever in a bind and you forget the formula for these things, right? It's not like, oh, I just can't do the integral. It's more like, oh, good thing I know how to derive this using u-substitution. You just derive your own formula. Let's come back around and do number 10 here. Number 10 says that the integral of dx over the square root of a squared minus x squared is equal to arcsine of x over a plus c. And this proof will be very similar to the one we just did, but we want to have a 1 here. It's the same thing we did in number 9, is we factor out an a squared to get a 1 here. Well, if we factor an a squared out of the radical, it comes out as simply a. So when we change this up, we actually have the integral of 1 over a, that comes all the way out to the front, of dx over square root of 1 minus quantity x over a squared. And now we can go right to our substitution here. So we can see that u is x over a, so then du is 1 over a dx, and then dx must then be a times du. Plugging that in up here for dx in the integral, and rewriting things a little bit, we now have 1 over a times the integral of a du over rad 1 minus u squared. And we are off to the races. Our a's cancel out, how nice. And we're left with the integral of 1 over u squared, which we know is arcsine of u plus c. But then recall that u is actually x over a, so this becomes arcsine x over a plus c, which is what we wanted to show. So I urge you to pick a few other integrals in the table, if you're up for it, and try to prove those. They shouldn't be too bad. And then from here on out, you can either use the table, or you can rederive these using u-substitution each time. It's up to you. It's probably best to know the table. It's going to save you some time, but the u-sub for these isn't the end of the world either.